is Tiago. Sorry, our next speaker is Tiago Enrique Picon from the University of Sao Paulo, and he will talk to us about Stein-Weiss inequality in L1 norm for vector fields. Go ahead, Tiago.
Thank you, Ursula. So firstly, I would like to thank the organizers for the invitation. It's a big pleasure to be here in MCA. So I'm going to talk about a Stein-Weiss inequality in L1 norm for vector fields. So this is a joint work with two colleagues from Argentina, Professor Harhoni, so working in Federal University of São Carlos in Brazil, and Professor Pablo de Napoli from Universidade de Buenos Aires, Argentina. So let me start fixing the notation. So here for us is capital IL is the His potential, so defined by the fractional integral given by this form. So L is the order of the operator. So capital N is the dimension of the Euclidean space. So let me present to you or remember you about the Stein-Weiss inequality is given by the estimate number 1. So this inequality is the boundaries of the His potential with power weighted. So in the P and Q estimate with power weight x minus beta, x alpha. So alpha and beta is alpha, beta, P and Q are related by in this relation. So alpha plus beta is bigger or equal than 0 is related to translation invariance of the inequality. So alpha and beta is bounded by n over p prime, and beta less than n over q is an integrability condition. So the focus in this talk is what happened in the case p equals 1. So I'm interested in the case p equals 1. So the case p equals 1 was not considered by Stein-Weiss. So the reason it's simple because the Stein-Weiss inequality fails when p equals 1 and, for instance, alpha equals 0. So the counter example is simple. You take the delta Dirac distribution. So first you take a approximation of identity. You define the phi is a CC infinity a positive function with integral equals 1. Then we apply the phi epsilon in the inequality. So the right side hand is uniformly bounded by 1. So then you take epsilon converge to 0. So the His potential of the modifier converges to the kernel of the operator, and this term is not integrable in LQ. So the counterexample, it's very simple. So although the Stein-Weiss inequality fails for p equals 1, some progress is still possible. So D'Ancona and Luca in 2020 proved the validity. In this case, if you assume some control of the support of the Fourier transform in the f hat on the annulus. So it's one possibility. The second possibility is you replace the power weighted to a general two-weight inequality for U and V measurable and positive. So in fact, this general inequality holds if only if the U and V satisfies some potential energy. In fact, you can replace U dx by a positive measure, and this term it's like a potential energy. So let me present an example. For instance, let me return to the original statement. When alpha, for instance, if p equals 1, so p prime is infinity. If p prime is infinity, alpha has to be less than 0. It is negative. But in fact, this case is covered by the example, because if you take the U equal modulus x minus beta q, V equal modulus y alpha, and the alpha is negative, and the alpha plus beta is positive. So you do this simple calculus. We split in two parts in a ball, outside of the ball. In the integration, use the alpha is negative, and this special case satisfies the previous control. Then you have the Stein-Weiss when p equals 1, but alpha is less than 0. Okay. So the Stein-Weiss with power eta can be written in this form. So in this form, I replaced the his potential by the integral form. So I replaced the kernel by xy. So very recently, together with Professor Ronis, we studied this inequalities of this type when alpha equals 0 in the setting of the vector fields when f is the image of some class of operators. For us, AD here is an elliptic and canceling homogeneous linear differential operator with order null in Rn, from a finite dimension complex vector space C to a finite dimensional complex vector space F. Let me tell you about, I will tell you what means canceling elliptic. I think you know about what means elliptic. Sorry, I have a small problem here. Okay. So the motivation about why study this type of inequality is a hardly told Sobolev inequality for this class of operator. So here this is a short extension of the hard Sobolev inequality, because we consider, for instance, the fractional derivatives of the Laplacian, and they consider general operator elliptic operators. In fact, this inequality recover the classical hard Sobolev inequality. If you assume, for instance, if nu minus L over 2 is an integer and k is bigger than 1, then is equivalent to the hard Sobolev inequality. If, for instance, the AD is a derivative operator. So in fact, if the operator has this special property, the canceling property, then this inequality holds. So in fact, the converse is true also. If the inequality holds, okay, the liticity is a necessary condition. In fact, if Q is bigger than 1, and the canceling is a sufficient condition. In fact, the canceling property characterizes this type of inequality. Okay. So let me press the definition of the liticity. Is a simple definition. You say that the operator is elliptic if the symbol is injective. It's okay. So the liticity is implied. You can write the fractional Laplacian like a green function. It's important to appear the ADU in the both sides of the inequality. Then you reduce your problem to prove some Stein-Weiss inequality in this setting when F is image of the operator AD. So now let me press to the definition of canceling property. What means canceling? So the canceling means that if you take the symbol, the image of the symbol, the operator, and you take the intersection of the psi in Rn minus 0, the intersection is equal to 0. So the rich theory of elliptic cancel operators is due to van Schaftgen. So this property, in fact, characterizes the Sobolev-Gallardo-Nirenberg when p equals 1. Let me tell you about this. So, in fact, we know that the classical result due to Calderon and Zygmunt in 1952. In fact, this inequality, you can compare the derivatives of the order null with operator homogeneous linear operator AD, if only if the operator is elliptic. okay, to compare the previous inequality, you have to pay some embedding, but it's embedding in LP, it's okay when P is bigger than 1. But the liticity is a necessary and sufficient condition when P is bigger than 1. The problem what happens when P equals 1, because Ornstein in 1962 presents a counterexample when P equals 1. So when P equals 1 appeared this canceling property. In fact, the canceling property characterized the problem when P equals 1. Let me present you some examples of canceling operators. If you take, for instance, the gradient operator, if you compute the symbol is identity, so it's elliptic, it's okay, it's 1, 1. So the canceling property is simple also, because if you take the image of the symbol, it is the R times psi. In dimension 1 is a real number times real number, so it's not 0, the intersection. But if you are in the 2-dimension or bigger than 2, so then you have multiplication of psi is a straight line passing through at the origin. So you have intersection of this line, the intersection is equal 0. Then this operator, the gradient operator, is canceling if the dimension is bigger or equal than 2, but is not canceling in dimension 1. So another example is the Korn-Sobolev-Strauss operator, is another example of the canceling operator. So another interesting example is the div curve. If you take D star forms, for general forms, the Hahn complex, so this operator is elliptic. It's elliptic. Okay, it's not easy to compute the symbol of this guy, but if you believe me, this is because it's not easy work in wedge product and the star is not easy. But if you believe me, this is the symbol of the operator. The liticity, it's simple because it follows from Lagrangian identity, and the cancellation follows by the standard property of the complex. If you have this D composed D is equals 0, D star composed D star equals 0, this is basically the idea that you have the cancellation property. Okay, the problem is the endpoint case, because when K equals 1, so you take D star, suppose that K equals 1 form, you compute the D star is a 0 form, and you apply the D star is 0, because the D star in this case is equal to 0. This is the problem to case K equals 1, and analogous to the case K equal n minus 1, okay? So another example is the higher order, if you can compose D star D and create a high order operator due to Loredana, Lassana, and Reich. So then you have another example in the higher order operators. So summarizing, in order to prove the Hardy-Sobolev inequality is sufficient, we prove this fundamental lemma. The fundamental lemma is a little difference to the Stein-Weiss, because K satisfies some control of the kernel, but it's basically his potential is not surprising, this assumption. But if you assume A is elliptic and canceling, then you have a type of Stein-Weiss inequality to a vector fields. So let me now present another type of operator. It's co-canceling operator. So the first is canceling, now is co-canceling. So you say that a homogeneous linear differential operator is co-canceling if you compute the symbol of the operator and take the kernel of the symbol and the intersection for every psi in n minus 0, the intersection is equal to 0. Okay. So let me present an important example is divergence operator. So divergence operator is co-canceling. So if you compute the symbol of this operator is basically the product. If you fix psi is the product of the the vector f. If you compute the kernel is simple, is the psi path, and you take the intersection is equal 0. Okay, so because if you fix psi, if you take in for every psi in Rn minus 0, the intersection are linearly independent. The intersection appear on only 0 belongs to the intersection. So this operator is co-canceling. So this is our main result. If you suppose that K has this behavior, it's likely his potential. And the news here is alpha is between 0 and 1. Because remember in the Stein-Weiss inequality, so when alpha is negative, it's okay. Alpha equals 0 is counterexample, but in this case, alpha is between 0 and 1. Okay, because we are in the vector space. Okay, so our result is the following. So if you suppose that a LD is some co-canceling operator, so this inequality holds if you take every f in the kernel of this operator. So if LD is co-canceling for every element in the kernel of the operator, satisfies this inequality. Okay, so problem. Yeah. Oh my God, I don't know what happened. Okay, work. So the first consequence is I can take the kernel of his potential because it's a simple corollary. So this is a version of the Stein-Weiss. If you suppose for if you have for every f in the kernel of some co-canceling operator, so it's a direct consequence of the previous result. But the nice thing is the converse, because if you have an operator LD, if you take f in the kernel of the operator and this inequality holds, then the operator has to be co-canceling. So it's very interesting because we don't know what happened when alpha is between 0 and 1, but in the case of alpha equals 0, we have the converse. So now let me press some applications of this inequality. So the first is a simple application, because you can extend the case of the hard inequality when alpha is between 0 and 1, is a simple consequence of the fundamental lemma when alpha is between 0 and 1. So the proof is applied the inequality, but the observation, the remark is that if you have a canceling operator, you know that if you take the f, the image of the canceling operator, the inequality holds. But the point is, what is the relation between the canceling and the co-canceling? Because if the operator is canceling, it's possible you construct some co-canceling operator, such that the kernel of this operator is the image of the canceling operator. So this is the point. The relation is the image of the operator A belongs to kernel of some operator. Then you connect the canceling and the co-canceling. Okay, so this is so let me present the second application. The second application is this this result due to Zhang. So Zhang, so assume some simple is a convolution kernel. So it's the same decay that we stated in the fundamental lemma. But the news here is this term in the inequality, because if you have a vector, if you have a vector in the vector setting, so you can have this inequality, is the Stein-Weiss inequality, but appear this term in another side of the inequality. But the new, it's interesting because when the divergence is equal 0, so divergence is a co-canceling operator. So F belongs to the kernel of the co-canceling operator, then you have the Stein-Weiss inequality. So in fact, we recover this result very easy because you can decompose a you can decompose the vector in two parts. So the first part is a standard Helmholtz decomposition. The first part, you decompose F equal G plus H. The first part with divergence equals 0, G. And the second part, H, it's a gradient term. So for G, it's okay because G is belonging to the kernel of some co-canceling operator, then you can apply the inequality. And the second term is a gradient term. So the gradient is a canceling operator. If it's a canceling operator, then you can apply the version of Stein-Weiss for the canceling operator. So it's very simple to recover this result. You can combine two parts for canceling and the co-canceling. The third application is the His potential boundaries in the hard space. Let me recall the boundaries of the His potential here. So no weight in inequality. So it's a standard boundary of the His potential. But the same problem appear in the case P equals 1, because P equals 1 is not possible. There is the same counterexample. But in the case P equals 1, it's possible to replace L1 for some subspace, such that it's possible to think about some space of L1 such that it is inequality holds. In fact, H1 here is not a Sobolev. It's a capital H is the hard space. H1 is the subspace of L1. So the functions in L1 such that the His transform is in L1. So this inequality, you can replace L1 by H1. This is the definition of the His transform. But very recently, Shikoha, Spector, and Van Schaften in 2017 so presented this inequality, and basically this inequality says that you can remove in H1 this part in the inequality, you can remove the part of L1. So it is too much. You think in H1 because you can remove this part. Okay, so then we recover this result with a simple proof. Okay, you can put in the general setting when alpha is between 0 and 1, but you can fix the original case when alpha equals 0, because you use the same method in the start. We replace the elitist, the idea to elitist to create the green function. We use the simple property of the His transform, the RJ squared, the sum is minus identity. So you can pass one RJ to another side and decompose with the His potential. Then you have KJ is the kernel associate of this guy, then is equivalent to prove some Stein-Weiss inequality in the special vector field RU. Is the His transform of U. So to conclude this inequality is only remark that we know that there is a special property of His transform. You can switch the derivative with the index of the His transform. So derivative x y rj is equal in distribution sense. So derivative x j r y. So if you define the f is a vector with the components, it's special these components fy rju fj minus r I, and another index is equal 0, then you have a vector space in the kernel of the divergence operator. So divergence is a co-canceling. You have the vector in the kernel, then you can apply the inequality and you recover the previous result of Skafte and Chico Heinzberg. So to finish, let me tell you some words about what is the magic of the canceling property or co-canceling property. What part appeared to prove the Stein-Weiss inequality? What is the magic part that solved the problem? So the proof is simple, because you take the kernel, you split in two parts, you localize one part. Is the standard proof in the harmonic analysis. So you localize one part and take another part it's okay, but this part, the local part, so you cut the kernel with a cutoff function, you localize the kernel, it's sufficient, you prove the inequality for each part, K1 and K2. So the K2, it's okay, is the K estimate is not difficult. But the first part is, I put in the red, so the magic is in the part, because if F belongs to the kernel of a canceling operator, so you produce some decay. This is the point. You have to produce some decay to obtain the nice integrability in the end. This is the point. So the point is, in several situations in the harmonic analysis, we expected the kernel solve your problem, produce some decay. So in this case, is the space is different. Okay. So this is the fundamental lemma, to produce some decay. If you take F in the kernel of some co-canceling operator, and you have a distribution, if you have a test function against F, then you estimate by derivatives of the test function in the polynomial. So disappear the term, the zero derivative disappeared. You produce 1, 2, 3 derivatives until the order of the operator, but the first, the zero order of the derivative disappear. So this is the magic to the canceling property. So to the second part, you use the kernel. The kernel is sufficient to produce the decay. Okay. So I'm finished here. So thank you very much.
Thank you very much, Tiago. Are there any questions?
I have a question. You talk about the problem in L1. There isn't any other problem related to the other endpoints in the Stein-Weiss inequality?
For operator, yes, because I didn't comment, but the operators, the maximum of the order the operator is the dimension of the Euclidean space. So the problem is when the order of the operator, for instance, for operators is associated to the vector associated to operators, when the order is bigger or equal than dimension. So this is another possibility, is think the similar to the case P equals infinity, because this is P equals 1. So you should think about the opposite when P equals infinity. But there is some work in this direction, but I never read the results to in the opposite, because P equals 1 is sufficient to last time to is sufficient to work a lot. P equals 1, but yes.
Okay, thank you, man.
Tiago again for his nice and clear talk. And
thank you.